All right. So for everyone joining this call, the call is being recorded. The organization organizing this event is the Minds, which is a peer mentoring group at the University of Bergen, more specifically led by the students of the Master in System Dynamics. And our goal is to help students aspiring modelers in their journeys in System Dynamics. But we also want to disseminate knowledge about system dynamics and reach different audiences and make it more well-known so we can help the field as a whole. My colleague Aidan will explain a bit our master.
Yeah, and so we are a combination. I know there's a small group of us here in person, but also some of us joining remotely as well. So we are a combination of master's students, full-time master's students studying system dynamics here at the University of Bergen. And you see there's two different programs. So there's two different, I guess, versions of us where together we're learning system dynamics. So some of us are full-time masters here in Bergen, where we spend 4 semesters completing our program, whereas some of us are traveling across to different universities here in Europe while also continuing to learn system dynamics. And so I just wanted to give a big plug for this, and you can learn more information by using the QR code below, or even reaching out to us through the email inserted on this slide, as we're beginning the application cycle for next year's cohort. So if you have students who are interested, or even if you yourself are interested and want to learn more information about how you can learn system dynamics alongside us in a more structured setting, I just wanted to give a quick shout out, because this has been a really fantastic opportunity, especially since we get to learn more about system dynamics and how it can be used outside of just school and academia. And I'll hand it back to you, Lucas. Thank you very much.
Thank you, Aidan. Well, I also would like to thank the System Dynamics Society, which allowed us to share this event on their website and reach more people. Like, we are so many today, 76 people. That's really amazing. Well, our agenda will consist 25 to 30 minutes lecture, followed by Q&A, and we'll try to keep it within 1 hour. For questions, since we are so many today, we have you can access the a pool website where you can post your questions and also upvote other questions, so you can filter which are the most popular questions. Hesham, well, I met you when I was studying in the Netherlands, but you have a very interesting CV and also a very research interest based on what I could find on your profile and also on the university website. You studied engineering, but also economics and political economics, and now you are a machine learner and system dynamics researcher at Radboud. But of course, we will ask directly to you about your past experiences, and that's all I have. I think we can get started. I will stop sharing.
Recording in progress.
Okay, thank you. I'm allowed to share.
Yes, I hope so.
Yes, can you see screen now? Okay, so thank you, everyone. Thank you, Lucas, for the invitation. I'm pleased to be part of this student initiative and also to be part again with System Dynamics Society. I think I had a work in progress not this year, in the international conference year before, and where I shared some parts of my research, and I will touch upon this lightly today. So thank you, and let's get to the table of content of what we're going to be discussing today. So I will be giving a brief about the machine learning applications available and the difference between AI, machine learning, and deep learning, the buzzwords in the AI community or in the AI field. And I will be talking about the threats that could be out there and the opportunities for working together or in parallel. This is something that we'll be discussing there. And I will share proposed approach that I'm working with some prominent name in the System Dynamics Society. So Etienne Rouet and Hubert Corlesius, we are working together with also Suzanne Howick and on an approach that combines system dynamics and machine learning. So I will share bits of it when we get to the opportunities, and then we will open the floor for discussion. So without further ado, let's start. So what is machine learning? So machine learning is basically a subset of AI or artificial intelligence. It's mainly concerned with training or programming computers to optimize its performance using data, time, and experience. And machine learning has two main core components, which are statistics and computer science. The role of statistics in machine learning is simply the inference from a sample, and the role of computers is mostly the efficiency in performing the task. So they are concerned with two main tasks. The first main task is to solve the optimization problem and to represent and evaluate such models in an efficient way. So this is briefly what machine learning is. Machine learning has three, let's say, common learning or machine learning applications, which are the unsupervised learning, the supervised learning, and the reinforcement learning. And we will be touching upon briefly upon the differences. So, because we will need this one in our discussion with combining it with system dynamics. So let's start with the most conventional approach, which is supervised learning applications. And in simple terms, supervised learning is a game of matching instance. So you go to the algorithm and you give the algorithm two main parts or two main aspects: the data itself, the data you want to categorize or classify, and the labels you have. So for example, I would give the list of attendees here and ask the algorithm to label them into, for example, male and female. And the algorithm will do nothing but matching all of the attendees here under either male or female. What if there's something else? Then this is an outlier, and a common application of this, what happened with COVID-19 pandemic, where the algorithms, where the medical algorithms were introduced to different symptoms, and these symptoms were not labeled under one of the categories, and they were labeled under other. And this is what it promoted the idea of looking further and seeing if this is something else. And the common problems in supervised learning, which I think most of the quantitative researchers are acquainted with, classification and regression. Some of the uses of such applications are the simple prediction of future cases and weather forecasting, outlier detection, as I said in the COVID-19 example, and data compression. The second most common application of machine learning is the unsupervised learning. And in this case, you go to the algorithm with only the data you have. So in the first case, in the first scenario, in the supervised learning, you presented your algorithm with two components: the data set you have and also the labels you want the algorithm to decide upon. In the case of unsupervised learning, you actually give only the data set and ask the algorithm to go on its own and cluster, for example, in one of the examples, cluster the instance you have. So in here, it's a game of looking for hidden patterns and the relations in the data. So the same example, I would give the algorithm the attendees list in here, and the algorithm will come up with clusters. And now you need to work in the reverse and figure out what your algorithm or the machine algorithm done. So they could be clustering the attendees here based on age in combination with height, in combination with, for example, educational status or level, and so forth. And your job after you get the result is to work backward and figure out what are the similarities between the cluster and there. Another problems or another application in there could be the association rules mining. And some of the examples or what we are using unsupervised learning for is the target marketing campaigns, for example, to give personalized campaigns to some segment of your customers and so forth, and customer segmentation, so marketing wide, and the recommendation systems is one of the examples of using unsupervised learning. The last common type of machine learning application is the reinforcement learning. And a famous example of this is simply the chatbots that you face with in commercial websites or medical chatbots, where you go to an agent or an algorithm and you give them the symptoms you have, and they try to give you answer. And by each answer or solution they offer you, they ask you, is it correct? Does it match what you are looking for? If you said yes, this is a reward. So the computer will store that, yeah, my solution, the first solution I proposed to the user is actually right. So it will be a reward, and agents or computers or machine learning algorithm here learn by accumulating rewards and storing it in its knowledge base. So this is how it works. One of the famous examples. So I would be going to, for example, a medical chatbot, and I will say the symptoms I have, and I will ask a question, and they will propose solution one or diagnosis one. And I said, no, this is not really what I have. And then they will propose another diagnosis. And I said, yes, this is what actually I have. And I confirmed the second one. The next day, another user has the same questions, the same symptoms will come in, and the agent now will start with the second solution or the second diagnosis they have instead of the first one, as they had a reward yesterday of learning that, yeah, the second diagnosis is more accurate when it comes to this specific symptoms and specific question. So some of the uses or examples of reinforcement learning is how to training robot and self-driving cars and personalized commercial and medical chatbots, which what we are exposed to now vastly, and the AI-powered stock buying and selling agents. Okay, so some of the buzzwords that you would have in research is artificial intelligence, machine learning, and deep learning. So what are the difference between the three? So in simple words, artificial intelligence is simply what contains everything inside. So, and artificial intelligence is using all the technological advancement, trying to mimic the human intelligence and how a human thinks. And machine learning is simply a part, as we said, part of the AI, and its main goal is to learn patterns from analyzing learning from large amount of data. So what about deep learning? Deep learning is also a subset of machine learning, and it optimizes the neural networks in order to find and learn patterns within data. So what is the key difference between deep learning and machine learning? They seem a little bit similar. The key difference is the human component or the human interaction. In machine learning, you have some sort of human interaction, as we saw in the reinforcement learning case, where the chatbot will go back to you and ask you, did I provide the correct answer? Did I provide the right diagnosis? And you will confirm with yes and no. And this is some sort of human interaction. And you can also intervene in the algorithm itself. In deep learning, the human interaction is little to none. So they work in its own. And one of the famous examples of deep learning is the GPT, or the generative pre-trained transformers. And the most common one is the ChatGPT, which now almost everyone is using. And the GPT are some sort or an example of deep learning. And that's why you saw the famous examples where, yeah, the developers of OpenAI had to update ChatGPT regularly, because some unforeseen events could happen with deep learning working in its own, and it sometimes get into a political scene or a biasness scene, and this is something that we will discuss moving forward. Okay, so I hope this clarifies the difference between the three. Let's now get into the threats, or what type of threats do we face. Now, I will start from a generic perspective. So let's address elephant in the room. Does technology advancement destroy jobs? Do they destroy our some sort of careers that we have? And are we, as people who work in system dynamics and even more widely working in the service industry, endangered with the AI advancement and technology advancement? The answer is not really. And I will use here a graph that I was shown by one of my professors back in 2010 when I was a student. And it shows that, yes, technology destroys jobs in some sector, but it actually equally or even more in a more advanced phase, they create more jobs. So as you can see here from the data from the US Bureau of Economic Analysis, you can see that the agriculture and industry somehow, let's start with agriculture from the 1840s, so more than 150 years ago, the agriculture has been declining in labor force, and machines are simply substituting them. However, at the same time, these machines are run by people or workforce, and also they are managed by engineers, and they are managed by, and they are being updated and served by more labor force. So actually what the technology advancements are doing is substituting the traditional or the conventional way of doing our daily task into more of a task or more of a job that requires more skills and more knowledge. So the key idea here, or the key challenge here, is how updated you are. So you must keep being updated with technological advancement, because sooner or later they might be risking your job or your way of doing your daily jobs. And you can see here in the industry, it peaked in the industrial revolution, and now the AI are caught up. And please bear in mind, this graph ended in 2010, so now it's even more further declining. But instead, the servers are now peaking and going further. So what are the challenges when we talk now more specific about the system dynamics and our practice in there? So we are eager to go for consensus in what we see. So we need a system that explains the situation, and where we can simulate how things are done. And then we can see whether we really capture everything or no in an organization or a problem. And this comes at a cost of, for example, one of the instances or the problems that we face is the power dynamics when it comes to the elicitation process of getting more of the ideas and the mechanism how things work in there. And you might face that, yeah, some of your stakeholders are simply imposing how things should be running from there. Another example could be the politics and scene in there. So I could be the production manager, and I'm more into, I'm the one who's doing the job. I know everything. You people who provide servers like marketing and sales departments, you don't really know how things are done there. And I have the challenge, I have the problems. We try to accommodate this by working with all the different stakeholders. We eager to go for this simulation or this version of reality where we can really infer something there. Another challenge or a threat there is a quantification of the unspoken. So if none of your stakeholders talk about a crucial problem there, and you couldn't really find it from the documentation and or the type of triangulation you try to do in order to represent the reality in an organization or so, you cannot really quantify something that you haven't been presented with. And here I wouldn't blame the power dynamics and politics. I've already, in my experience, met top management manager where they don't really know what the problem is. So sometimes it's not about the power, it's about also the knowledge. So they have a problem that they cannot really have a spot or put their hand on. So this is a challenge that you need to also bear or go through. So let's jump into the opportunities or the other side. On the other side, machine learning, and now I'm speaking on behalf of many people, and also it's proven in the research that sometimes machine learning is being treated as a black box methodology. So you put an input, there's something happening inside this black box, and you have the output. And opacity, which we call opacity. And this is something that is widely known, or a fear or a threat that is widely addressed not only in the academia but also in the industry, where managers don't really like to rely on algorithms because they don't really know what happens inside. I hope with my introduction on the AI, machine learning, and deep learning, I tried to clear the air a little bit there into showing you which are the black boxes, and which are the, let's say, the statistics aspect of machine learning. So this is one of the problems. A second common problem that is widely documented in academia is objectivity and biasness. So this goes against the selling points of machine learning. We're saying data is objective, numbers are objective, you cannot really go wrong in there. However, in reality, this is not the case. One of the most famous cases that was reported by Obermeyer in 2019 about the racial discrimination in the algorithm managing the health population. Here in the Netherlands, we have also a famous case where the child care allowances were hundreds of thousands of parents, 26,000 of parents were penalized with fines as they committed fraud, but in reality, the algorithm was somehow biased against the people from different ethnicity groups and who are not really Dutch. So biasness is already there in machine learning, and one of the key problems that happened there, or the main reason for this, is simply feature selection. And feature selection. And feature selection is, in simple terms, for people from different domains, is the variables or the attributes or the columns in my table. So the different attributes, you need to select them. And in machine learning, you have to provide an output. You could be having millions and billions of data. So where are you going to start? This is where the decisions or the micro decision come in. And the person who designed these algorithms make micro decisions there. And when you make micro decisions there, it could lead to subjectivity in your process, in the development phase, and it could lead to biasness or bias in your approach that will be reflected in your data. So actually in machine learning, having too little data is bad, and also having huge data is not always good, because you need to make decisions. And based on these decisions, you could be ending up in one of the cases where actually algorithms that was supposed to bring justice and transparency in the process actually did the opposite and provided discrimination and bias in your process. So what are the meeting points? So now we know what are the threats or the criticism from people who comes from outside the system dynamics community, and also people who come from outside machine learning or AI pro community. There are actually points of complementing one another. So let's start with system dynamics. So a system dynamics model is created to understand patterns from data, but not only from data, which is similar to what the AI or machine learning does. System dynamics model, when we create system dynamic models, we actually go beyond into incorporating the human factor represented by expertise, knowledge, and law of natures or conventionalities in the different type of domains. And this is something that machine learning fails to do, or does it in a limited approach. So actually, this is part of the book chapters that will be published next year. So it's again in cooperation with system dynamics figures here, like Hubert Corozielos and Etienne Rouet and Professor Suzanne Haug. And we also have application in the medical field on the Dutch elderly healthcare system. And here we combine these two methods into addressing the challenges, or let's not say the weaknesses, or the point of improvement in each method. So machine learning could really benefit from this starting point of feature selection and where to look for. And also machine learning can provide, and also system dynamics can provide the expert knowledge to machine learning. And in return, machine learning can really quantify the unspoken, can go for the underlying hidden patterns in the data and how they are interacting with what you are doing and how to proceed forward. We propose in our book chapter, and hopefully it will be published next year, 5-step approach where we integrate the two methods together. So we always start from the system dynamics model. Here we're talking about the qualitative models that usually elicit ideas and information through group model building sessions. And this qualitative SD model is usually the starting point for the data analysis, where it provides a better approach of the feature selection. Feature selection is done usually in machine learning using only algorithm, which is not always ideal. And then the quantification of both the known variables and the unspoken variables or unspoken realities. And in the fourth step, we refine by either adding or subtracting or taking out some of the variables in the qualitative model, and we turn it into enhanced model. And based on this model, we create a prediction model that hopefully combines both. We are in the step 4 now of our application, and hopefully this will be also an article that's published next year, but by the end of next year, where we apply our approach in the medical field, in the elderly healthcare system, the Dutch elderly healthcare system, to see the visibility and the result of applying such approach and what are the benefits of using both. So we are now hopefully in the middle of our application. The book chapter is almost done and the analysis there are already done. So hopefully we're waiting for the publication process or the editorial process, and it will be there. So one of the main strengths that we have in this approach is simply that we try to strengthen each method by enhancing their ability and getting the best out of them. And hopefully when this chapter is out, I will open the discussion in a bit, and hopefully when the chapter is out, we provide more example, and I will provide more example in our discussion, how these two are integrated in a way to provide or enhance both methods in terms of predictability or the predictions that they can provide. So I will open now. I've taken for quite some time now, so I open the floor for the discussion, and during the discussion I will provide more details on the research and the examples I talked about now.
All right, I just taking some time to unmute myself. Well, we got a few questions on the pool, but on the pool website. But if you also want to, if someone also wants to post on the chat, is also fine, and we will manage here. The first question is, could you elaborate more on how to apply ML techniques for feature selection using SD qualitative model? Would you translate the qualitative model into algorithms to build the ML model, or would the SD qualitative model serve as a boundary to build the ML model?
So yeah, good question. Actually, this is where I will start with example from our proposed approach or our work. So we started with an SD qualitative model that was illustrated from a GMB session or a group model session, and we asked a simple question. We started the session with a simple question: what do you think are the variables that influence cognitive decline in elderly people? So, what type of variables influence people to decline more in their journey of eventually losing their cognitive abilities? And we came up with variables, and these variables were between 15 and 18. So we did a couple of sessions, and the shared version was 18 variables, and these 18 variables are simply variables that could be represented in the data. On the other hand, we have the data from the elderly people, and they are more than 1,000 variables. So you can see the difference between what the experts have their opinion on in terms of variables. Some of the 1,000 variables could be combined into 3 or 4 clusters that could represent one of the variables expressed by medical doctors. But yeah, we take these 18 variables and we start to represent them in the data or make clusters from the variables we have in the data, and we start with as a starting point. On the other hand, you could have, without doing so, you could have started with 1,000 variable that you have in the data, or 1,000 plus, and you would get results, but they are not really concise to what the medical doctors need or your domain of experts need. So what we provide here is more or less a service. So you need to answer what your clients need. So our clients in this case was the medical doctors. So just going into hidden patterns using machine learning without really starting point or feature selections that would provide a good starting point is simply swimming in an ocean and you don't know which direction you are going to. So you might step on a good patterns, but they will not be as much of a relevant to your clients or the people you are trying to address. I hope this answers your question.
We have a question in the room.
Yeah, now you can hear. The screen is a bit messed up here. We have too many screens.
Yeah, thank you. My name is Konstantin. So when I was talking previously about combining machine learning and system dynamics, my biggest concern was that you're losing a part of the process, that you're losing the learning that you get in the process of discovering the system, of drawing the model. But in this proposal here, it seems like it doesn't necessarily even have to be a problem. But then could you please elaborate more on the interaction between the qualitative model you do and the outcome of your machine learning algorithm? What does this outcome actually look like? And I understand that it's an iterative process between human and machine creation. So when you get an outcome from the algorithm, what does it look like, and how do you work on that? Like, how do you further develop it?
Okay, I want to clarify. So you're asking now about our proposed approach, right? Or in general?
Yes, your proposed approach.
Okay, so we start. So the first step is simply sitting with a domain expert, in our case, a medical doctor, and we try to elicit the variables they think are more important or the most important in influencing people when they are going down in their cognitive decline. Usually people above or patients above 65 years old, and we get the information in a traditional system dynamics model or CLD model, or causal loop diagram model. And we have all the variables and the interaction between the variables with our dependent variable as a cognitive decline. And now we have the interaction. You could, what you traditionally would do is to quantify this and by the means of system dynamics and simulate it over time to see the different influences in there. What we don't do the quantification part, we do an additional part, or this is where the machine learning kicks in. So we take this qualitative model with the variables identify and the relation in there, and we do similar to what the system dynamics does, which simply quantifies the relation there between the variables. And we go with the extra mile of discovering the hidden data or the hidden patterns within data. So there are variables that was expressed by the doctors, and we have found through the data analytics. So we started with the 18 variables provided by them. We did a pre-processing and data cleaning and so forth. And we started, and now one of the examples would be that we identified another arrow or another relationship that wasn't really identified before. And we say, like, in terms of our process, we see that there are relationships in there, and it's a strong one that could explain some of the decline in one of the variables or one of the aspects in the patient's life. And we go back to the doctor. Again, we're not doctors. We go back to the doctors. This is what the data says, and it could add something to what you have already expressed in the first, for example, group model building session. And we go back to them and say, yeah, they can either confirm or say, no, this is purely coincidence, and this is not really describing any of what we are trying to express in here. And this is the first part. And also the doctors or the domain experts provide what they are really interested in. So they see all the hidden pattern and say, like, okay, there is a pattern number 2, 3, 4, and 10. These are interesting for us. Could you go back and apply another algorithm or another machine learning, or go back in your data analysis process and try to explore more and dig more into what type of knowledge or information can you extract from here? So in this case, the data analysis process or the machine learning process is actually driven by the domain expert or the domain knowledge rather than just purely the algorithm. And there is a famous example in this, which is a clustering quality control we have in machine learning, where the algorithm itself, when you give them data, they will tell you the ideal clusters for you is 3. But in reality, 3 are very little, because you are looking, for example, for the outliers or for the minority or the underrepresented clusters or group of people or group of patients in the data set you have. So you are actually not looking for how they can cluster people with their similarity, but rather you are looking for something hidden. If you go to doctors, they already know the most common patterns, and they can tell you, for example, that, yeah, if you have this type of gene, your cognitive decline will most probably be going down fast or slowly. But this is not what the doctors actually are looking for. They are looking for the hidden patterns or the patterns that are not obvious there. So here you use a machine learning or a system dynamic qualitative model as a starting point to save time and look into the areas where your domain experts are interested in. And also it benefits again when you give the results back to your domain expert, and then they guide the process of the data analysis rather than letting the algorithm guide the process of finding patterns. I hope this clarifies your question.
Yeah, we have a follow-up question.
Yeah, thank you. So it's really great to hear how you really make this process participatory. But also, just to make it clear, could you speak a bit on how you actually apply the machine algorithm. Not so much the technical part, but in terms of what are the inputs, what does the output look like? Like, do you provide the CLD, or do you look at relationship between single variables? And is the output like a fully quantified model? Is the output only covering the relationship between certain variables? How does that work?
Okay, so yeah, thank you for the question. So yeah, I can walk you through without much more in the technicalities part. So we extract the variables we got from the doctors, and each variable, this is the reality, and this is the pre-processing part, which we spend 60% of our time doing. So each variable identified by, if your life is super easy, these variables can be represented by columns or variables in the data, which is not the reality. Each variable is usually represented by a combination of 5 to 6 variables in your data, and you need to combine them, and you need to go back and sit with the doctors to agree on how this can be streamlined and transformed into one, for example, valuable number or meaningful numbers that you can really use in your analysis. So my job, or we start with pre-processing and cleaning the data, and assigning variables to assigning features. We call it machine learning features to the variables identified by the doctors. We have to agree in this. Sometimes you have a missing data. Sometimes your data is not actually corresponding with this. So I will give you a really example experience from our research. We started with data from the Netherlands, which what we are trying to solve the problem with, but we couldn't find as big data to really make inference from the sampling there. So we had to go for a different data set from a different country or a different region. In our case, it was data from the USA, and we had to make some transformation in there. And most of our analysis of the data technique or the machine learning techniques were applied there, and we go back to the doctors and they either confirm or say, no, this is not an interesting pattern, please leave it aside. This is something I'm more interested in. So we go back to the data analysis process and we try to dig more in there in order to get more information. And as you said, it's a participatory approach. And one of the main reasons of using system dynamics as a method is the participatory aspect out of it. And this is what really machine learning methods as a method.
Yeah, quite interesting. Thank you for your answers, Hesham. We have one answer from the online people. Is there a question? Sorry, is there a way that machine learning could be used to create system dynamics model from just data? For example, you feed data, patients moving through a healthcare system, and the ML come with a set of SD-style equations that can capture a certain reference mode more accurately. And I would like to combine it with 2 other questions. If you are able to use a data set to it, how would you differentiate between the different types of variables that we have in SD and then replicate the reference model?
Okay, so good. Actually, thank you very much for this question. And I have to distinguish between what this actually presentation is about. This is about machine learning as a method and system dynamics as a method. Your question is more of can I do system dynamics model by the means of machine learning? The answer is simple. It's absolutely yes. And actually in R, one of the programming languages we use for machine learning is R is a statistical programming language. And there are something called package. So R works with packages. And actually there are packages there where you can represent everything you do in system dynamics in there. And you can use, as a means of artificial intelligence and machine learning in predicting and working with variables. And you can absolutely do a conventional SD modeling in there using the tools of machine learning. But for me, this is not what I'm interested in, and this is not actually what I apply. I actually I address machine learning as a method and how it can complement the system dynamics and the other way around, rather than trying to do what we already can do on Vincem or any of the softwares that we could use in the system dynamic community, and do it with machine learning tools. There are benefits, but I find them not really as enriching to the process or the experience of really working with system dynamics model or tools, as if you are really approaching machine learning as a complementary method. I hope this clarifies the difference. And the answer is yeah, you can do so, but the benefits there are not really as much.
Yeah, that's a great answer. Thank you.
We have another question online, which is, all models are inherently biased. It depends on the choice of variables you choose the variables you choose to include in your model, and how you can help mitigate this problem. So basically, how could you how can you debias your models, basically?
Yeah, actually, this is again, it depends on the skill set or the tools you would have, but this is why we are integrating the two methods. So you could find some set of biasness that could be injected in the process from the system dynamics perspective. When there is one version, there is power dynamics in there that imposes some sort of scenarios that are put in there that they end up in your model. And machine learning can assist in this way into giving you some running the same scenarios and giving you some patterns that comes only from the data. I wouldn't say the data would be completely objective, but combining the finding from the data with the real scenario you hear from your stakeholders is something that can shed the light or give you more information into how the real scenario is. So in this case, you will start with system dynamics and the variables there, and they can provide their own biasness. I agree with you, and system dynamics can do so, but the process of triangulating there and the process of having biasness in machine learning is totally different. The bias in the design of the biasness that you would have from system dynamics. And this is what we try to propose, that actually you can mitigate both by combining the findings from here and there in order to get closer to or try to be as objective as you can.
This also answers a follow-up question, which was about efforts or considerations that you, if people, researchers who are applying AI to SD are thinking on ethical considerations of that. Would you like to comment on it, whether there is an ethical framework being developed and how you deal with it during your research?
Yes, of course, there is always an ethical framework that you work with, and your decisions can really vastly change everything. And there are already well-proven examples of the use of machine learning or AI where discrimination and racial bias is already injected in the process just because of, I wouldn't say a mistake, just because of certain steps that they were taking in the design phase. So ethical framework is a dilemma that we have to work with. We try to mitigate as much as we can into getting to objectivity as much as we can get. So we get the scenario from the stakeholders, we get the scenarios from the data, and we combine both, and we try to use them. I wouldn't say as a leverage to make your stakeholders admit something, but rather as discussion points or a starting point of a discussion where you can open the book a little bit to get to the real problems or the underlying problems in what you're trying to address.
Yeah, thank you. I have two questions which I think we already touched upon, but perhaps the the people who are asking want to know it in more detail is how the ML distinguishes between correlation and causation, and then how you would distinguish between stocks and flows from the data, like perhaps a more technical aspect on how you deal with it.
Okay, but I can share. So the second one is easier to answer. I can share. There are packages where you can really do so. So it's done for you. It's now it's much more easier when you want to apply a traditional system dynamics model into machine learning tools like R or Python and so forth. So there are packages to do so, and they have their own documentation where you can see how they are represented in there. And let's go to the first one. And now I have to go a little bit technical there. So causation and correlation, this is something that we touch upon even in my teaching here in Radboud University. So one of the common algorithm in machine learning where this problem actually occurs is association rules mining. And let me put it in simple words. Association rules mining is simply what the big companies are doing for all of us as the clients to understand our purchasing patterns. So they go into transactions and they try to see what product is sells with what, and based on what type of promotion I can do, I can increase my sales and so forth. So you can have, for example, coincidence in there that everybody, or like let's say you have a confidence that 98% of people who buys cheese, they will buy bread. So from the transaction, from the association rules mining that you performed in machine learning, you had this rule that 98% of the people who buys cheese will definitely buy bread. Only 2% of the transactions, these two products are not combined. And you could be saying, wow, this is something great, and I found something. And in reality, this could be only because these products are commonly bought, so you can always find confidence between the two, but it doesn't really explain anything. And it's similar to when it, for example, when it rains, people who are with, for example, Alzheimer, when it, for example, in Nijmegen, the temperature goes down, the people have more cognitive decline when the temperature goes down. This is something that can really, show significance in the data, but it's not really causation in there. So in what we do in machine learning, this is a technical part, we assess something called left and support. And left, for example, this is one technical aspect of the association rules mining. It tells you whether the rule you had or the rule you had, like for example, in our case, the cheese and bread, is it really a rule or it comes by coincidence? And this is something that can really be applied in there. And we teach to our students here when they go for the introduction to big data applications. And yes, there are tools. And again, machine learning makes your life easier because you can really go for some sort of algorithms that can really identify whether the rule you have is simply causation or correlation.
Well, thank you very much for your explanation, Hesham. It definitely answers the question, at least on my side. Well, we are almost to the end of the hour, and I would like to ask you if there is any question which we didn't ask you, but that would still be relevant to understand this topic, or that you would like to develop further.
Yeah, there's it's a hope. So this is why I'm here. I hope that our session sheds a light on machine learning, and I hope it's not treated as a threat or as a black box. This is something that you can really accompany in your toolkit. For me, I consider myself as one of the newer generations in the SD society, so I'm one of you. I'm not an expert. Yeah, I have a little bit of experience in the machine learning and the AI field throughout my professional career, but I consider myself someone of the new generation. And what I really want to pass on to almost all of us that we have to keep an open-minded when it comes to technology advancements around us. And this is something I learned early on in my career. The more you have in your skill set or toolkit as someone who, as a system dynamist or a modeler, the more you have, the better you have an understanding. So it will serve you in both ways. It could be that you would use it in your own work, or you can really answer criticism in a better way because you have understanding.
Thank you very much for your final comment, Hesham. Well, we don't have further questions online. Most of them seem to be answered now, so thank you very much. And as on the side of Minds, I'd like to thank you for giving us your time. That's very kind of you, and we're very, very pleased to have you today, and also to everyone who joined from home. This recording will be available on the Minds channel on YouTube. And we also have another talk there, and we always post further events on our LinkedIn page. And we aim to also share them on the System Dynamics Society. So yeah, thank you very much.
And thank you for all the attendees. And yeah, I look forward to any further question. You can reach me over email, and you can always, we can always have a discussion. I hope I don't expect that everybody accepts the idea, but yeah, let's keep an open mind and we discuss together. So thank you all.
Thank you very much. Everyone have a nice day and nice weekend.